Today we explore a fascinating paradox in materials science: why charged microcapsules rupture instead of simply swelling. pH-responsive microcapsules are tiny spherical containers that respond to changes in acidity. They contain charged polymer chains that should expand when ionized, but something unexpected happens. Let's start by understanding what these microcapsules are and why they matter. Microcapsules are tiny spherical containers with polymer shells. Their diameter typically ranges from 1 to 1,000 micrometers, which is incredibly small. 1 micrometer equals 10 to the negative 6th meters, or 1/1,000,000th of a meter. Inside these capsules, we can store various materials like drugs, enzymes, or other active compounds. The polymer shell protects the contents until triggered. These microcapsules have exciting applications in targeted drug delivery, food preservation, and even self-healing materials. The key to understanding this paradox lies in pH-responsive polymers. pH-responsive polymers contain special groups that can gain or lose electrical charge depending on the acidity of their environment. pH is defined as the negative logarithm of hydrogen ion concentration. Lower pH means more acidic, higher pH means more basic. The pH scale ranges from 0 to 14, with 0 being extremely acidic, 7 neutral, and 14 extremely basic. A common example is polyacrylic acid, which contains carboxyl groups. These groups lose protons and become negatively charged at higher pH values. The chemical reaction shows a carboxyl group losing a proton to become negatively charged. This is fundamental to the behavior we're investigating. So what should happen when these polymer chains become charged? Let's think through the physics. When polymer chains in the capsule wall gain electrical charge, the like charges should repel each other, causing the chains to stretch apart. We expect the capsule to swell as the charge groups push away from each other, expanding the overall structure while maintaining integrity. The swelling pressure can be calculated using Donen equilibrium theory, which describes ion distribution across semi-permeable membranes. The osmotic pressure pi equals RT times the difference between ion concentrations inside and outside the capsule, where R is the gas constant and T is temperature. But here's the paradox that puzzles scientists. Instead of simply swelling, the capsules sometimes catastrophically rupture and disintegrate. Let's dive into this counterintuitive phenomenon and understand what's really happening. When the charge density is below a certain critical threshold, instead of uniform expansion, the capsules rupture and fall apart. With low charge density, the capsule doesn't expand uniformly. Instead, it develops cracks and ruptures, with fragments breaking away. Why does this counterintuitive behavior occur? Let's ask ourselves, what forces are competing in this system? To understand the paradox, we need to analyze the competing forces acting on the capsule wall. 3 main forces determine whether a capsule swells or ruptures: electrostatic repulsion, elastic resistance, and surface tension. First, electrostatic repulsion between charged groups pushes outward, trying to expand the capsule. Second, the elastic resistance of the polymer network pushes back inward, resisting deformation. Third, surface tension acts to minimize the surface area, pulling the capsule inward. The total pressure equals electrostatic pressure minus elastic pressure minus surface pressure. The balance of these determines stability. Let's quantify the electrostatic repulsion that drives expansion. Charged groups on the polymer chains repel each other according to Coulomb's law, creating an outward pressure. The force between two charges equals 1 over 4 pi epsilon naught epsilon r times Q1 Q2 over r squared, where epsilon r is the relative permittivity. For a charged polymer network, we can estimate the total electrostatic pressure by integrating over all charge interactions. The electrostatic pressure scales approximately as charge density squared times electron charge squared divided by the permittivity. Let's work through a numerical example. Assume a charge density of about 1 elementary charge per cubic nanometer. This corresponds to a charge density of 10 to the 27th per cubic meter. Plugging into our formula with water's dielectric constant of 80, we calculate the pressure. This gives an electrostatic pressure of roughly 360 kilopascals, or about 3.6 atmospheres, which is substantial. Now let's examine the elastic resistance that opposes expansion. The polymer network behaves like rubber, resisting stretching through entropic elasticity of the polymer chains. The elastic pressure equals the shear modulus G times V over V, not to the negative 5/3 power, where V is current volume. G is the shear modulus of the polymer network. For typical hydrogels, this is around 10 to 100 kilopascals. As the network stretches, the polymer chains straighten out, losing entropy. This creates a restoring force proportional to the extension. For small amounts of swelling, the elastic pressure increases roughly linearly with the volume change. The third force is surface tension, which tries to minimize the capsule's surface area. Surface tension creates a pressure equal to 2 gamma over r, where gamma is surface tension and r is the capsule radius. This is the Young-Laplace equation. For a water-polymer interface, the surface tension gamma is typically around 0.05 newtons per meter. Let's calculate the surface tension pressure for a capsule with a 10 micrometer radius. This gives 10 to the 4th pascals, or 10 kilopascals, which is about 0.1 atmospheres. Notice that surface tension becomes more important for smaller capsules because the pressure scales inversely with radius. Now we can understand why there is a critical charge threshold for rupture versus swelling. At high charge density, the electrostatic pressure is strong and uniform throughout the network, causing smooth, uniform swelling. But at low charge density, the charges are sparse and tend to cluster. This creates regions of high stress and weak spots in the structure. Compare high charge density with uniform distribution versus low charge density, where charges cluster together, leaving regions with little support. We can estimate the critical charge density by analyzing when mechanical stability breaks down. The critical charge density scales as the square root of G times permittivity over E squared times correlation length squared. Here, Xi is the correlation length of charge fluctuations, typically a few nanometers in polymer systems. Let's dig deeper into the mechanism of rupture through stress concentration. When charges cluster together, they create localized regions where electrostatic stress becomes very high. A cluster of charges creates strong repulsive forces, all pushing outward in one localized region, concentrating stress. These localized stress concentrations can exceed the mechanical strength of the polymer network, initiating cracks. When local stress exceeds fracture stress, rupture initiates. This is the key criterion for capsule failure. Once a crack forms, it propagates rapidly through the structure due to stress amplification at the crack tip. The crack propagates, splitting the capsule into fragments as stored elastic energy drives the fracture process. For a more rigorous understanding, we use Poisson-Boltzmann theory to describe charge distribution. The equilibrium charge distribution inside the capsule wall follows the Poisson-Boltzmann equation. The Laplacian of electric potential phi equals negative charge density over permittivity. This is Poisson's equation. The charge density follows a Boltzmann distribution. Rho equals rho naught times exponential of negative E phi over kBt. Combining these equations gives the full nonlinear Poisson-Boltzmann equation that governs electrostatic behavior. This nonlinear equation determines the electric potential and charge distribution self-consistently. For weak charging, where the potential is small, we can linearize this equation using a first-order expansion. The linearized form gives a screening length that characterizes how charges distribute themselves. This introduces an important length scale called the Debye screening length. The Debye length equals the square root of permittivity times kBt over E squared times charge density. For typical ionic concentrations in water, the Debye screening length is about 1 to 10 nanometers. Let's analyze this problem from an energy perspective using free energy. The total free energy of the system has three main contributions: electrostatic energy, elastic energy, and surface energy. Total free energy F equals electrostatic free energy plus elastic free energy plus surface free energy. The electrostatic free energy is stored in the electric field and scales with the square of the charge density. Electrostatic energy equals the integral of permittivity times gradient of potential squared over 2, integrated over volume. The elastic free energy increases as the polymer network deforms from its equilibrium configuration. Elastic energy is proportional to the shear modulus times the sum of squared stretch ratios minus 3. Surface energy is simply proportional to the total surface area of the capsule. Surface free energy equals surface tension gamma times area A. For the capsule to be stable, the total free energy must be at a local minimum with respect to small perturbations. At equilibrium, the derivative of F with respect to radius equals 0, and the second derivative must be positive for stability. Below the critical charge density, there is no stable minimum in the free energy landscape, and the system evolves toward rupture. What do experiments tell us about this paradox? Let's examine the evidence. Experimental studies show a sharp transition between the swelling regime and the rupture regime as charge density changes. This graph shows capsule radius versus charge density. Below the critical point, capsules rupture. Above it, they swell smoothly. The exact position of this transition depends on polymer crosslink density, pH level, and ionic strength of the solution. Increasing the crosslink density of the polymer network makes it more resistant, shifting the transition to lower charge densities. This paradox has important practical implications for designing drug delivery systems. For controlled drug release applications, we want gradual swelling that releases drugs slowly, not catastrophic rupture. The design strategy is to ensure the charge density always exceeds the critical threshold during pH changes. By ensuring sufficient charge density, we can engineer microcapsules that swell predictably, releasing their cargo in a controlled manner.